discussing a recently published paper, Pi0, a vision language action flow model for general robot control, Sergey Levine et al. Sergey introduced the paper at the Trimble podcast. That's how I came across it. It's published. The links are in the show note, both the interview and the paper, both highly recommended. I think this is, in my opinion, a pivotal moment for us. It's a pivotal moment for the robotics community because it's the first attempt in a large-scale academic distributed way to create a general purpose robotics model. Now, I'm going to dissect all these terms, but just for starters, what we're trying to do here is have a model that can be given to a robot, and then the robot can execute tasks without having been specifically trained for that task. Sergey goes way out of his way to make it very clear that they're standing on the shoulders of giants here, and the giants are the large language models. So what happened with the large language models community is, ever since at least ChatGPT came out, but even before that, but definitely with ChatGPT, we understood one fundamental big lesson, and that is that we can have models that are trained to do math, trained to do poetry, trained to do history or whatever, or we can have a general model which is trained with a transformer backbone, and it turns out that the general model is better at the specific tasks. That is the big insight. Now, when we translate this to robotics, actually it becomes much more acute how great this is, because in robotics, the problem with training specific tasks has been around for years, if not decades, definitely for years. I've started following the space seriously probably about 4 years ago, and I've noticed one thing, that almost every presentation I go to still today is kind of like the opening a bottle presentation, the putting a cup in the cabinet presentation. And like one of the professors I spoke to at NeurIPS recently said, that's what gets you tenure in robotics. Solve the opening beer bottles problem. Solve the cleaning a room problem. In other words, everything is task specific. And that, on the one hand, is very cumbersome, very difficult, because when we talk general in robotics, or the inverse of general, which is specific, we're not just talking about some sort of abstract specific versus general way. General means a lot of things in robotics. It means general environment, general embodiment, general task. What does it mean to open a bottle? Does it imply also pouring the beer into a glass? Or even more extreme, what does it mean cleaning a room? Well, what is that? So these are all very sort of fundamental problems that robotics has had to grasp with for years now. And what Levine et al. Are trying to do here is start, in my opinion, what they're doing here is sort of the beginnings of the Linux of robotics, the beginnings of Spark of robotics, the beginning of RiskV of robotics. So this is a very Berkeley-esque thing to do, right? We're going back to the fundamentals. We're building a distributed, large-scale, fundamental way to solve a problem, and then hopefully the community jumps onto it, and we have an open source. This is, the chronopunks in the 70s, which were the predecessors of Bitcoin. Like, this is very Berkeley-esque. And I think this, just as a side note, just shows how a culture in a place like Berkeley, or a university in general, can be really strong, really, really strong. And I think kudos to, I don't have to, for regular listeners, I'm sure I don't have to reiterate how impressed I am with the work that Berkeley is doing in robotics, particularly Sergey, Peter, Jitendra, and many others. They're not just interesting and impactful, they're inspiring. And that's, to me, that's the biggest accolade you can give to any kind of scientist, or anybody who does anything for that matter. So back to the Pi0 paper. So what is the Pi0 paper trying to do? It's explaining an approach that is trying to generalize robotics in a way that large language models have generalized language. So this is the fundamental idea, and I'm going to discuss the details in this episode. Hopefully I can do justice to this really, really interesting work. This is not even on podcast. It's February 19, 2025. This is Krimdelko. For the year, we are down 9%. The market's up 4.5%. We're underperforming by 13.5%. So let's jump right into the paper. Pi0 is a general purpose compute for robotics. The goal is to have a robot and tell the robot, go open this beer bottle for me. It goes, opens the beer bottle, go clean my room, go clean my car, go pick up the groceries in my car. We want to do a zero-shot prompts and have it execute the task. The same way we have zero-shot prompts now for things like LLM or Grok or Claude, where we can just ask, okay, what is the difference between diffusion model and something else, right? It gives me the answer. I don't have to prompt it. I don't have to help it out with question and answers. I can do a bit of chain of thought and things like that. But in general, the models are pretty good, particularly at relatively simple tasks, like, for example, answering, okay, was Napoleon actually defeated at Trafalgar or not? And what happened there? Like those are, and then at the same token, I can ask, pun not intended, I can ask, okay, how do I really make a really good satay chicken? Like it can do all these things one after the other in the same model. The weights are there, it's been trained on a large amount of data, and it can reproduce this amazing result. So what Sergey is trying to explain in the interview is really the approach which they use, which is piggybacking on the large language model experience, right? Let's use a lot of data and pre-train, and then let's fine-tune. There's a couple of things that they did which are really interesting. I want to point out two things. Okay, three things. First, what is the pre-training? The pre-training is based on a vision language model. Vision language model, in other words, they're using the knowledge that has been generated through the large language models, and then later on vision language models, they're using Gemma, a family of models that helps, it's a vision Gemma model. Gemma is a large language models by Google. And the vision language model is, I forgot something with P and then Gemma. Doesn't matter, these words. I don't want to get entangled with these things. Fundamentally, what they're trying to do is, okay, they pre-train the model with the vision language model. What is the vision language model? It just says, okay, there's a chair. This is a chair. Please go and pick up the pillow, which is on that chair, and put it somewhere. So there is a language instruction accompanied with image. Now the robot in the real world has, let's say, a camera, and it sees the chair. It understands what's going on because it has been pre-trained on the vision language model. And what they're adding now is an action. It's an action expert. In other words, they're using a mixture of experts architecture. The action experts is a diffusion-based trained action model. What that really means is the following. The same way we have diffusion for image generation, we could have diffusion for action generation. Action and image, in essence, are the same thing from a computer perspective, because all it does, it looks at something and tries to reproduce that something. That's what image generation is. Now, instead of reproducing a pixel, an amount of pixels, it reproduces an amount of actions, which again are vector coordinates. Vector coordinates are translated into actions. So using 50 hertz, so each time step has 50 different vector coordinates that translate into action, and that action is allows for high dexterity. So this diffusion approach allows for high dexterity. So what that means in practicality now is the robot sees something, gets triggered by a language prompt, go pick up the pillow, which is on the chair, and put it in the cabinet. And then the actual execution of the task, the action itself, is a bunch of proprioceptive coordinates, proprioceptive sensor measurements, which translate into vector measurements, which then turn into actions. So this is roughly the architecture of the whole thing. I think there's a couple of things that Sergey talks about. One is the recipe. What does he mean with recipe? A lot of things in robotics is still sort of nascently, in a sense that we are still trying to argue, let's say, what kind of data should we actually use in the pre-training phase and what kind of fine-tuning should we do? One interesting thing that Sergey mentioned is that in the pre-training phase, what you want to have is lots of diverse data. So for example, when we train a robot, you know, I recently listened to Palmer Luckey and the Anduril sort of approach towards defense, and he was talking about humanoid robots in the battlefield. So he said you can have an Navy SEAL robot that is as agile, as fast, as smart as the best AI models available. So how do we pre-train a model for a robot to be a really good sharpshooter and also really good at carrying people, wounded people, and maybe even helping them out in a medical way? Well, what we want to have is we want to have lots of experts and also lots of not so good experts data. Why? Because we want the robot not just to learn from the best in the pre-training phase. We want the robot to learn from mistakes also. In order to be able to recover and learn from mistakes, the robot has to have seen some mistakes and then be able to recover from that. So that's one really interesting insight. In the fine-tuning phase, however, we want experts. Because the fine-tuning phase is now, okay, you figured out that you're on the right path. Now, how do you actually execute, let's say, sharpshooting? How do you make something, or, shirt folding or opening bottles and all that stuff? So that's really an interesting insight. The other interesting thing in the recipe section of the paper, which I think Sergey talked about, was the tokenization. That's a really interesting question, not just in the large language model space, but definitely in the robotics space. And what Sergey pointed out here is that in terms of tokenization, first you have to ask yourself, okay, what exactly are we tokenizing? Let's say when it comes to the action expert, are we tokenizing vector coordinates? And then what kind of coordinates are we using? Are we using angles between vectors? Are we using the length of the vectors, or are we using some sort of cross product of the vector? What is the tokenization that we're actually using? And most interesting in terms of tokenization, what he said is that it's also very important to sort of kind of normalize the tokens. And what you don't want, like the same way with data, it's the same with tokens. You don't want certain tokens to overwhelm sort of the token space. And therefore, you want to kind of normalize those tokens, which I don't know what that actually means in technical implementation, but conceptually, what he's trying to say here is that we don't want certain tokens to overwhelm the system and sort of become overfitting for certain specific signals. So we want to make sure that these tokens are in some way or form normalized. So I think that, to me, that's just something that I paid attention to that I thought was really interesting. So to summarize, Pi 0 is a beginning. It's an approach towards a new form of general robotic learning. I think really important, particularly for us, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. We at Orange Capital Partners, we are highly invested in real-world AI, in the robotic space, and in particular in AI. So we're not too much interest. We don't have too much interest in robotics as a field as it was until now. What we're really interested in is the robotics going forward, which is learnable robotics, intelligent robotics. These types of robots, the same way that Sergey's team explains it, like robots that are really flexible and dexterous and intelligent and can act on the moment. Now, I know at least a while ago, Sergey expressed the wish to build some sort of Robinson Crusoe robot. So a robot that you can drop the thing somewhere and it can actually start building its own survival kits and all of that stuff. In other words, it can trigger its own purpose. Now, we're not there yet, of course. This is just the beginning. But I think the way I said in the prelude, to me, this reminds me a little bit of the Linux, Spark, RiskV, Chronopunks. Like, this is the beginning of a field, the beginning of a decentralized, open source way to solve a really big problem. And I think what they're doing here, very much in the sort of traditional Berkeley, is they're trying to sort of build a snowball here. And I think this is very, very important. I think also for us here at Orange Capital Partners, the question always comes back to, okay, how is this going to turn into wealth generation? Because the purpose of our fund is to invest in fundamentally new concepts and engineering practices with large impact. That's what we're doing. We have large positions in Tesla and NVIDIA. We're interested in companies like Anduril, which is private. We're not invested in Anduril. But those types of companies that are leveraging AI and mechanical engineering and fluid mechanics and physics towards new applications for whether it's defense or consumer products, transport, to do really important things, help our defense, lower the cost and increase our effectivity, help our energy landscape to transition to a more sustainable energy future without giving up on comfort. All of these things are very important. And I think this paper really fits well into this, of course, because, for example, Optimus is the kind of computer architecture that, in my opinion, should be piggybacking on this. I think finally what I want to say is something that we discussed a couple of times, which is the concept of transfer learning, which is sort of embedded in this paper. Okay, the idea of a general purpose model for robotics also means that there's some sort of transfer learning, some emergent learning that comes from different types of skills. And the transfer learning idea that we had a while ago, which I think is really what's so exciting about Tesla, is that the FSD, Tesla FSD, is the first real-world AI that works, is being used by hundreds of thousands of customers every day, and it's not used in any kind of geofence, teleoperated way. So this is certainly the first real-world intelligence that humanity has ever seen at scale. Now, why is Tesla investing so much in Optimus? In our opinion, that's because there is transfer learning from the FSD problem, which is a navigation action problem. It's photons in and actuators out, and it's mainly about navigation. And we believe that there's a transfer learning from navigation towards robotics, because the robotics problem essentially is a navigation problem. If you look at the action expert in this Pi0 model, it's actually a navigation problem, right? How do my hand needs to go to the bottle, grasp the bottle, and open the bottle? These are all navigation problems in essence, right? How far away am I from the bottle? Where's the bottle? How do I grasp it? How do my fingers grasp? So those are sort of navigation. So the idea, again, is that the transfer learning is really what's so exciting, and that gives us a bit of an edge as Tesla investors. We hope that that is what Tesla is leveraging. We've discussed this several times with the Tesla teams. They're sort of tight-lipped about it. I believe it's not because they don't want to say it. I think they're not so sure that they're actually using transfer learning from FSD towards Optimus. But it's there, it's possible, and I think it needs to be exploited. Now, whether Tesla jumps on this Pi0 bandwagon or not, that is, of course, up to them. We believe that this is a very, very important first step towards an open source distributed type of general purpose robotics learning, which will give a huge boost to robotics infrastructure, the robotics field, and also hopefully help us better navigate the robotics and the real world AI world that we believe is the future of intelligence, because real intelligence is interaction with the real world, because the real world is the best oracle for how your AI is actually able to predict and navigate throughout the world. Thank you.